teammates, we are the team number 1, and it's conformed by
Erasmo Guerrero,
Jennifer de Horta, Miriam Lomelí,
and me, González. The topics in these presentations were the next, 4-bit adder, 8-bit adder, subtractor keys 1, subtractor keys 2, and we're going to present subtractor combinations. Adders. Binary adders are arithmetic circuit in the form called adders and full adders, used to add together two binary digits. The difference between half adders and full adders is that half adders has only one gate XOR and only one gate AND. Full adders has two gates OR, XOR, and two gates AND, and one gate OR.
This 74LSA3, how we can see in this image, is how physically we are going to connect our inputs or outputs. For example, here we have A1, and here is B1. Here it is where they make the addition, and the output is here, as the same as for A2 and B2, and here is the output, and everything is the same, just that here we have ground and the carry. Here it's how it's built internally, the way they are. This logic symbol is like this. We can draw it like this, putting A0, A1, A2, A3, and the other number B0, B1, B2, B3, and our outputs will be here, our carry here, and this will be connected to ground. So here we have the subtractor combination. We use two circuits integrated. This one, the 74LS83, and the other one is the same. But here we have the connections of 4 NOT that are in the connection of A, and this is next. We have another NOT, and we have some XOR. This helps to obtain the results in two cases: when A is higher than B, or when B is higher than A. With this connection, we can obtain of the results. It looks harder, but it is easy. And it's a little bit complicated than the others because we use some XOR, but we can make a lot of, well, the subtraction when the A is higher or the B is higher.
To build the circuit that we make in multisim, we need some logic gates that are not logic gates and XOR logic gates, and we compare ourselves. The subtraction that we are going to perform is that one, and we solve it using the complement to 1, and it is the result. We are gonna solve this simulation, and we're gonna check the outputs to confirm that the result is correct. We have the values in the inputs for the first adder, that is 0, 1, 1, 1, as is this same value that we have in the subtraction. Then we have the negation of the second number, that is, well, without the negation we have 1, 0, and 0. But it is negated, we have 0, 0, 0, 1, and 1. And then the sum, the addition of these inputs will be that one. And then for the output, we get 0, 1, 0, 1 in this same order that we have S1, S2, S3, and S4. And this same order that we have over there is the same that we have in the output. So we have 0, 0, 1, 0, 1. Well, as we can see here, we have 0 in the carry, and then it means that we have a 0 connected with another adder. Then we use another NOT logic gate to connect the XOR logic gate. This means that all of those XOR logic gates has the negation of 0, that is 1, connected to all of those XOR logic gates. So we have 0 here, no, it's 1, 1, 1, 1, and 1. And the outputs from this other are connected to each one of the XOR logic gates. So we have then, when we have 1 and 1, the result of the XOR logic gates is going to be a 0, because, as we remember, only when the inputs are different, we are going to get a 1. So, for the outputs, we have 0, 1, 0, and 1. And this same result that we have here in the outputs of the logic gates, we have in the inputs of the other adder, that is 0, 1, 0, and 1. And as we have the B connected to ground, this is the result that we have in the output of the second adder. As we check, 0, 1, 0, 1, this is the output, and we can check that it's correct with the lens that we have here.
Well, this is an example to realize it really quickly. As my partner said, we have others, 74LS83. We have two, this and this. To realize it, we have an operation that is a subtraction. If we have this operation, we need to realize by a complementary to this. That means if we have this, we need to write them like this, and the second is the opposite. That means 1, 0, 0, 1. The result is 1, 0, 1, and 1. and here we have 0. This is a current. That means that we need to put in here. Well, but to represent this is A3, A2, A1, and A0. B3, 2, 1, and B0. This is the order that we need to put for this. The output at the right will be S0, S1, S2, S3, and the carry that is 0. As my pioneer Erasmus said, here we need we have a logic gate node and so what happened with this is that if we have a 0, the opposite of this is 1. That means if in the XOR we have two pins, and all of them we have a 1, and in the second pin we have 0. Here we need 4 combinations. In this case, if we have 1 and 1, that means in the output we obtain 0. That means if we have at the same time 1 and 1 or 0, 0, the output we obtain 0, but it's different when we have 1 and 0 or 0 and 1.
Well, just an observation. We had some problems with the images. We draw all the scans that we had. Some of them we took from the internet, from some pages.
In my conclusion, this information is based in the intelligence science, because if we don't have this, the automatic area doesn't work.
In my conclusion, using this is better than using the subtractor in case A or B because it can make both, and just with this thing circuit.
In my conclusion, if we know how these circuits work, we can make a lot of addition or subtraction, even when these circuits are only for additions. We just have to know how it works, and that's it.
In my conclusion, I find this topic very interesting because we use others to perform a subtraction with the combination with the logic gates. It's very interesting because in this case, with the combination with case 1 and case 2, we have to perform both of the cases with the same circuit, and it is very interesting, the connection between the logic gates and the others.
And then, in my conclusion, I think it's very important to know why and how it does of this subtraction working, and to realize more of them, and to realize different types of diagrams in our major.
Any question?
Do you have any questions?
No.